There is a ticking clock hanging over our entire global digital infrastructure. For decades, our data has been secured by mathematical fortresses that honestly seemed completely impenetrable. But with quantum computing advancing at an incredible pace, moving away from just theoretical math to actual practical breakthroughs like Google's Willow chip, well, that fortress is starting to crumble. We're facing a real deadline, expected right around 2030, where large-scale quantum computers could just break traditional encryption entirely. But the good news is, there is a solution. In August 2024, NIST, the National Institute of Standards and Technology, finalized the very first post-quantum cryptography standards. So in this explainer, we're zeroing in on exactly what those new standards mean for us, and specifically how the two primary algorithms, ML-KEM and ML-DSA, differ in their real-world application.
All right, to make sure we've got a clear roadmap for how we're going to navigate this whole transition, here's the agenda. We'll start with how the quantum threat actually breaks our current crypto, then explore the immediate danger of harvest now, decrypt later attacks. After that, we'll hit our main focus, the critical differences between ML-KEM and ML-DSA, followed by their real-world applications. And finally, we'll wrap up with the hybrid migration strategy you can actually start using today.
So part 1, the quantum threat and the end of RSA and ECC. Let's really look at why our current tools are suddenly becoming obsolete.
Okay, let's dive into this. Since about 1977, algorithms like RSA and a bit later elliptic curve cryptography, or ECC, have basically been the gold standard. They secure virtually all of our digital communications. And they work because they rely on incredibly difficult math problems, things like factoring massive prime numbers. For a traditional, classical computer, breaking an RSA 2048-bit key would take literally billions of years. But quantum computers? They play by a totally different set of rules. Using something called Shor's algorithm, a sufficiently powerful quantum computer can solve those exact same math problems in what's known as polynomial time. Basically, that means it reduces billions of years of computing down to just a matter of hours, or maybe days. It completely shatters the foundation of RSA and ECC.
Now you might be thinking, okay, but that kind of quantum power is decades away, right? Well, consider this number, 500,000. Recent research actually indicates that breaking ECC 256, which is a hugely popular standard today, might only require about 500,000 physical qubits. That brings the timeline for cryptographically relevant quantum computers way, way closer to our present reality. It makes this a problem we absolutely have to solve right now.
Which brings us to part 2, harvest now, decrypt later. This is the immediate, high-stakes threat facing every single organization today.
Let's walk through how this works, because it brilliantly illustrates why waiting until 2030 to upgrade is a terrible idea. In a harvest now, decrypt later attack, or HNDL, bad actors are actively intercepting and hoarding your encrypted data right now, in year 1. Sure, they know they can't read it yet, but they don't care. They just sit on it. They wait until year X, when that cryptographically relevant quantum computer finally comes online. And then, in year X+1, they simply decrypt all of those historical secrets. The actual attack is happening today. It's just the payoff that's delayed.
So, the big question is, who is most at risk here? Basically, any data that holds its value over a long period of time is a prime target. We're talking corporate trade secrets, next-gen R&D, long-term financial contracts. But you got to think about the hardware side too. Aerospace systems have lifespans of like 40 years. 5G and 6G telecommunications infrastructure will be operating for 20 to 30 years. If a medical device with a 15-year lifespan is deployed today using vulnerable cryptography, its data is exposed for a massive, lingering vulnerability window.
All right, part 3, ML-KEM versus ML-DSA. These are NIST's new post-quantum cryptography standards, and the core focus of our explainer, how exactly do they differ when we actually apply them.
To really wrap our heads around their distinct roles, think of public key cryptography like a tool belt. You wouldn't use a hammer to drive a screw, right? In this new quantum-resistant tool belt, ML-KEM is basically the lock on the door. It protects the exchange of the secret keys that keep your conversation private. ML-DSA, on the other hand, is the signature on the guestbook. It proves exactly who you are and guarantees that your message hasn't been tampered with along the way.
Let's see how this builds out technically. ML-KEM stands for module-lattice-based key encapsulation mechanism. In practice, you're going to use ML-KEM when two parties need to agree on a shared encryption key over a public, untrusted channel. It is a direct replacement for classical algorithms like ECDH. Conversely, ML-DSA stands for module-lattice-based digital signature algorithm. Its application is strictly for authentication and integrity. We're talking TLS certificate signing, code signing, and verifying sender identity. It replaces ECDSA and RSA PSS. So even though they're both based on the exact same family of lattice math, their jobs in your network are fundamentally different.
Now, we do have to talk about the primary engineering trade-off we're accepting for all this quantum safety, because it is massive. Think about classical ECC public keys. They're incredibly tiny, usually around 32 bytes. But to resist quantum attacks, the underlying math has to be way more complex. ML-KEM 768 requires public keys of over 1,100 bytes. And ML-DSA? Its signatures are absolutely huge by comparison, nearly 3,300 bytes. That is roughly 51 times larger than classical ECDSA. This sheer size increase is really the #1 challenge engineers are facing when trying to deploy these new tools.
And because the digital signature use case is just so critical, NIST actually provided a backup standard, SLHDSA, or FIPS 205. Now, unlike ML-DSA, which uses that lattice math we just talked about, SLHDSA relies entirely on the hardness of standard hash functions like SHA-2. It is an incredibly conservative, highly secure safety net. The trade-off, though, is that its signatures are even larger, so its primary application is really reserved for things like firmware updates and root certificate signing, situations where having the absolute maximum security easily outweighs pure performance.
Moving into Part 4, Real-World Applications. Let's shift our focus to how these algorithms are actively disrupting and upgrading global IT and telecom networks.
A recent GTI analysis of telecom networks paints a really clear picture of this impact. Interestingly, symmetric cryptography just needs its key length doubled to stay safe from quantum computers. But asymmetric crypto, or public key signatures and key exchanges, those are entirely insecure. And modern 5G core networks rely heavily on those exact asymmetric algorithms for completely vital functions, like authenticating users and managing mobile handoffs. Without migrating to ML-KEM and ML-DSA, the entire security foundation of 5G essentially falls apart.
The crucial takeaway here is that this migration touches absolutely everything. Because ML-KEM and ML-DSA have those much larger sizes we discussed, your everyday TLS handshakes on the web are going to increase by 1 to 2 kilobytes. For a modern broadband connection, sure, that's fine. But for bandwidth-constrained IoT devices or remote smart meters, trying to accommodate a 3 kilobyte ML-DSA signature is a massive struggle. Furthermore, the entire global public key infrastructure, every single certificate authority out there, has to transition to these new standards. That means widespread protocol updates across SSH, IPsec, and beyond.
Finally, Part 5, the hybrid migration strategy. Given all these massive infrastructure challenges, how do we actually deploy this without just breaking the internet? Let's look at the strategy.
The absolute foundation for surviving this transition is something called crypto agility. Listen, if your organization hard codes RSA directly into its software, you're going to have a very bad time. Crypto agility means building systems where the cryptographic algorithms are modular. You need to be able to swap out an old algorithm and swap in ML-KEM or ML-DSA simply by tweaking a configuration file, rather than having to undertake some massive, expensive code rewrite.
And this brings us to what is easily the current industry best practice, the hybrid key exchange. Right now, major players like Google Chrome and Cloudflare aren't just instantly dropping classical math. Instead, they're running a classical algorithm like X25519 simultaneously with a post-quantum algorithm like ML-KEM 768. They combine them into a single shared secret. Why is this so brilliant? Because it guarantees you quantum safety today while still providing that proven classical safety net and backward compatibility for older clients during the transition. It's the best of both worlds.
Okay, let's lay out an actionable roadmap for the IT professionals tuning in. Step 1. Enable that exact hybrid key exchange, X25519 combined with ML-KEM 768 in your TLS 1.3 configurations today. Step 2. Verify that your internet-facing servers, load balancers, and gateways actually support it. Step 3. Relentlessly test for backward compatibility to make sure older traffic falls back gracefully. And Step 4. Start planning with your vendors right now for when PQC certificates using ML-SDA become fully standardized and trusted by browsers, because that is expected to happen very soon.
We've covered a lot of ground today, right? From the highly distinct applications of ML-KEM for key exchange versus ML-DSA for signatures to the urgent, pressing reality of the quantum timeline. I want to leave you with this final provocative thought.
Because of harvest now, decrypt later attacks, the quantum threat is absolutely not a 2030 problem. It is a today problem. Are your organization's long-lived trade secrets and private communications already sitting on a server somewhere, just waiting for a quantum computer to unlock them? It's time to begin your cryptographic inventory today. Thanks so much for joining me on this explainer, and I'll see you next time.